Hello friends, in last video we ended up with a cost function. Cost function is an error function, and in formula cost function is equal to e1 square plus e2 square plus dot 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 up to en square. Here error is equal to actual value minus predicted value, where actual value is coming from the data, so we can't change it, and predicted value that we can decide. So predicted value was y, and y is equal to sigmoid of x, where x is equal to w1 m1 plus w2 m2 plus b. Here w1, w2 and b are weights and biases, and m1 and m2 are height and width data of flower. So x becomes function of weight and bias. And if x is function of weight and bias, then ultimately cost function will also become function of weight and bias. For simplicity, let's remove b. So our cost function c becomes function of w. Now remember this neural network. This neural network was taking height and width as an input, and it was giving color value as output. Weight and biases was acting as a parameter in this neural network function. But cost function is different. It is taking width and bias as an input, actual data as a parameters, and giving one number as output. And this number decides how bad our neural network is performing. If this number is big, then neural network is performing bad. And if this number is less, then neural network is performing good. So our goal is to reduce this number as much as possible. If we plot graph of cost function versus parameter by assuming that there is only one parameter, then it may look like this. It can have many lower points, but out of them we want to find the lowest point, and that lowest point is known as global minima. All other lower points are known as local minima, and our goal is to find this global minima. But before that, let's understand basic mathematics behind it. You may have heard this equation y is equal to mx plus c. This is equation of straight line. And if I want to plot equation of y is equal to x square, then I will have a curved plot. Now suppose this is the cost function and we want to find minima of this function. For that purpose, let's start with any point. Draw a tangent line at there. Find slope of that line. And that slope is also known as derivative of a function at a given point. If we move forward and take slope at another point, then it will be little less. If we again move forward and take slope at this lowest point, then we will have a flat line and slope will be equal to 0. That means dy by dx is equal to 0 and y is equal to x square. So d upon dx into x square is equal to 0. Now let's understand power rule of derivation. D upon dx into x raised to n is equal to n into x raised to n minus 1. And if n is equal to 2, then it will become 2x. At this point slope was 0, so 2x is equal to 0 and eventually x becomes 0. So at the point x is equal to 0, function is taking its minimum value. From this exercise you might be thinking that finding minima of a function is very easy. Just take a derivative, make it 0 and calculate the x. But in actual it's not that much easy. Real world functions are much more complex. They are having multiple parameters in thousands and lakhs, and because of that it is also not feasible to plot them, and they does not have any algebraic solution. For example, take this equation x square plus x is equal to y. This is simple equation and it can have algebraic solution, so x value we can calculate from this formula. But if function is that much complex, like 2 into x raised to 5 plus 3 into x raised to 4 plus 9 into x raised to cube plus 7x is equal to y, then we can't solve this algebraically, because there is no way to isolate this x. So wherever algebraic solution fails, algorithm comes to rescue. Algorithm is a step-by-step iterative process to find the solution. In our case, that is minima of a function. To understand gradient descent algorithm, let's take an example of mountain. Suppose you are on a mountain and there is a foggy environment. So you can see only your nearby distance and you want to go to the downmost point of the hill. For that purpose, you can take small steps in visible area in downwards direction. In that, you need to have two things: step size in some direction and speed. Here, step size with direction will depend on the slope. If slope is big, then step size will be big. If slope is less, then step size will be less. And speed is something that you can decide by your own. So in this case, our algorithm becomes xn is equal to x minus eta dy by dx. Now see this, if we want to find the slope at p1, then it can be calculated like this: y2 minus y1 upon x2 minus x1. And for the point P, dy by dx is equal to y2 minus y1 upon x2 minus x1. At P1, if we calculate the slope, then it will have a negative value. And at P2, if we calculate it, then it will have a positive value. So at P1, if we have negative slope, then we will move towards increasing direction of x. And at P2, if we have a positive slope, then we will move towards decreasing direction of x. Now see this gradient descent algorithm. Here, x is parameter and y is function. Our parameter is weight and function is cost function. So let's denote x with w and y with c. So our gradient descent algorithm becomes wn is equal to w minus eta del c upon del w. This is the main algorithm that we need to use. If we plot a graph of cost versus parameter by assuming there is only one parameter, then it may look like this. It can have many minima points. If we have started from here, then we may end up with this local minima point, and if we have started from here, then we may end up with this global minima point. It means that there is no guarantee that we will end up with global minima always. So as a solution, we can make this process iterative. At which minima point we end up, that totally depends on from where we have started. So we can start from multiple points repeatedly, and we can make this process iterative. This will increase our chances of reaching at global minima eventually. Here we can choose step size by our own. If we choose step size too slow, then it can take more time and it can become computationally expensive. If we choose step size too fast, then it can have a diverged behavior and we can never reach to the point. If we choose large fixed step size, then we may overshoot the point. So the best choice is to select a step size that is decreasing. In decreasing step size, eventually we will reach to the minima point. So that's how gradient descent algorithm is working. It is an iterative process which is starting from multiple points and eventually it is reaching to the global minima point with decreasing step size. So that's it for the gradient descent, and formula is Wn is equal to W minus eta del C upon del W, where eta is the learning rate that is deciding the speed and del C upon del W is given by the slope, and that is also contribution in the error by that weight parameter. Goal of this gradient descent algorithm is to optimize the parameter by reducing cost. That's why it is also known as optimizer algorithm. Now we know our what, why and how. What we want to do. We want to update the parameters. Why? To reduce the cost. How? By using gradient descent algorithm. So that was it for the gradient descent algorithm. This was a very simple example by having two input and one output in single neural network. But real neural network are very complex than this. It has layered architecture in which there is one input layer, another is output layer, and in between there are multiple hidden layers. So we get error in the output layer, and that error needs to be propagated up to the first layer. And that is done by backpropagation algorithm. And we will look into it in detail in next video. Thanks for watching this.